Operating a national power grid requires matching the exact amount of electricity generated with the exact amount consumed, second by second. Inside the National Grid Control Room, operators monitor this balance. To protect against sudden faults, they maintain a standing reserve of 1,000 megawatts, enough backup generation to replace the single largest power plant on the network if it suddenly goes offline. At 16:52 on August 9, 2019, a massive lightning strike hit a high-voltage transmission line in Cambridgeshire. The physical safety hardware operated exactly as designed. Circuit breakers isolated the strike and cleared the electrical fault in less than a tenth of a second. That routine weather event caused a momentary voltage dip across the network. That split-second fluctuation initiated a chain reaction that pushed modern automated systems beyond their limits. At the Hornsea One offshore wind farm, overprotective software detected the voltage dip. Interpreting the fluctuation as a critical error, the control system rapidly slashed the farm's power output. Nearly simultaneously, at the Little Barford gas plant, the same electrical disturbance caused a discrepancy between two turbine speed sensors. The plant's automated safety logic triggered an immediate shutdown to protect the machinery. This chart's sharp drop shows the initial 1,300 megawatt loss from Hornsea and Little Barford, burning through the grid's reserve. This frequency drop triggered localized embedded generators, like solar and diesel, to automatically sever from the grid, erasing another 500 megawatts. Every piece of physical hardware was fully functional, but isolated software systems across the country, programmed to protect specific equipment, reacted to the anomaly by shutting down, creating a massive collective power deficit. With supply plummeting, the frequency of the alternating current in the grid went into freefall. If it drops too far, the entire national network enters a death spiral, causing severe physical damage to power stations and a total system collapse. To prevent total failure, the grid relies on a last resort protocol called Low Frequency Demand Disconnection, or LFDD. LFDD is an automated mechanism that intentionally cuts off power to entire regions to force supply and demand back into balance. This chart shows the program's trigger thresholds for demand disconnection. When the system frequency hit the Stage 1 threshold of 48.80 Hz, automated relays immediately severed power to 5% of Great Britain's demand. In a fraction of a second, over 1 million customers lost electricity. Entire neighborhoods went black, hospitals lost power, and businesses were plunged into darkness. To arrest the fall in grid frequency, the automated amputation successfully stabilized the national grid. By shedding that load, the power system survived, but the sudden disconnection exported the crisis directly into other critical infrastructure networks. Grid operators restored electricity to all customers within 45 minutes. For the railway system, the disruption was only beginning. Modern Class 700 and 717 trains are equipped with highly sensitive onboard software. When the train's computers detected the grid's split-second frequency drop, they executed a permanent lockout, an extreme safety protocol that completely disabled the train's electrical drives. Because the lockout was permanent, drivers could not restart the engines. Dozens of trains were frozen on active tracks. Recovery required dispatching technicians on foot with laptops to manually reset the software on each individual train, forcing the cancellation of hundreds of services. With tracks blocked and schedules ruined, massive crowds backed up at major transport hubs like St. Pancras International. Passengers faced severe delays that rippled into the following days, entirely due to isolated software protocols. The grid's automated systems succeeded by shutting power down to protect the network. The train's automated systems protected their electrical drives by doing the exact same thing. Both systems worked perfectly in isolation, but failed spectacularly in combination. Following the blackout, operators patched the control software at the wind farm and updated the train's onboard computers to tolerate wider frequency fluctuations. Adjusting those specific thresholds addresses the symptoms of August 9th, but it leaves the underlying vulnerability intact as infrastructure grows more complex. The energy grid is transitioning from a system dominated by a few massive coal and gas plants to a decentralized energy system. This is a network where power is generated by thousands of independent, localized renewable sources and battery nodes. Operating the grid with thousands of automated endpoints requires a shift in how safety protocols are designed. Software can no longer act in blind isolation. It requires an intelligence capable of understanding its place within a vast interconnected ecosystem.